Okay, the quiz, I'm actually going to go over that problem, but the quiz I handed back to you while you were taking the quiz, I had initially thought I was going to grade it just like if you got one problem right, that would be good. But I had enough people get both problems right on last week's quiz that I felt like, okay, I'm going to count it off of 2 questions. So a lot of you got one of them right, not the other. Don't let that discourage you. But, you know, if this one quiz comes back at the end to haunt you and it's like between a letter grade, we'll work something out, all right? Just for now, keep working. This quiz here, integration by parts is what I was looking for, right? What is the u and what's the dv here? ln x is a good u. dv would be everything else there, which is x cubed dx. Then du over here is 1 over x dx. And v would be 1/4 x to the 4th. And the reason that works out so good is because ultraviolet minus voodoo, ultraviolet's just those two multiplied, but your new integral is going to have this times this, which is going to wind up being like an x cubed, which will be easy to integrate. So here's where we are. This equals ultraviolet, I'm going to write it this way, 1/4 x to the 4th natural log x minus integral v du. So 1/4 x to the 4th times 1 over x dx. This equals 1/4 x to the 4th plus natural log x minus 1/4 integral x cubed dx. And finally, the antiderivative of x cubed is 1/4 x to the 4th. So you have 1/4 x to the 4th natural log x minus 1/16 x to the 4th plus a constant. Everyone see where the 1/16 comes from? That's it. Any questions on that one? Good. All right, so any questions on homework?
Kind of.
Okay, what do you got?
On number 9, I just used substitution at work.
Did you use the formula that we derived at the end of class for natural log? Okay, then that's fine. Because we came up with that formula, right? Okay, that's okay with me. Any other questions? Go ahead.
Can you just work it out?
What, number 9?
Yeah, the long way.
Okay, I'll do it the long way. Okay, the long way would be to act like we don't know what the antiderivative of natural log of u is. Like at the end of class last time, I did this, right? And I gave you a formula. It was u natural log u minus u, right? Plus c, that formula from last class. But let's act like we don't have that. And let's try integration by parts. We're here. I'm going to choose, well, what did you choose? Or did you choose anything?
For you chose ln.
Okay, ln of 2x plus 1, right? Now, don't ever choose dx by itself to be u. Because then what's the derivative of u? It's the derivative of dx, which would be d dx, which I haven't shown you anything like that before, right? So this is a good choice of u. That forces your dv to be what?
dt.
dx, right? Is the problem t?
It's t, yeah.
In the original problem? Is it t? Whatever, I'm going to do x's. Is that all right? Okay. So what is u prime? What's du over here then? So 1 over 2x plus 1 times, be careful here, the derivative of what's inside. You have to use chain rule, right? Derivative of natural log of something is 1 over it times derivative of what's in there. What's the derivative of what's in there? 2. So how about I put 2 over instead? And then dx. With me? Now what's v? X. Okay. I'm ready to use my formula. So ultraviolet is x natural log 2x plus 1, right? That's u times v, minus integral of v. V's real nice, isn't it? X times du, which is 2 over 2x plus 1 dx. Is that good? But this is the same as x natural log 2x plus 1 minus integral 2x over 2x plus 1 dx. And at this point, you kind of look at that and you go, what do you do with this? You can't split it into two, right? Because you have two terms on the bottom, one on top. You maybe would try integration by parts again, but the cleanest thing is just to make a substitution. Like pick u to be equal to the whole bottom, 2x plus 1. And then what's du? 2 dx, right? So let me rewrite this. I'm just going to take this integral right here. I'm going to rewrite it over here for a second. Does anyone have a question though where I am on this? Real good? Let me take this integral real quick. Integral, I'm going to rewrite it this way. X over 2x plus 1, 2 dx. Now the reason I wrote it that way is to kind of stress the 2 dx, right, is going to become a what? That's going to become my du, isn't it? And then the 2x plus 1 is going to become my u, isn't it? And the only thing I need to still resolve is what's going to happen to my x. So I can go back to this equation right here, right, and solve it for x. So take this equation here, subtract 1 on both sides, and then divide both sides by 2, or multiply both sides by 1/2. I like multiplying by 1/2. Why? Because that 1/2 I'll be able to factor out. So let me rewrite the integral. X became what? What's this x? 1/2 u minus 1 over, what's the bottom? U, what's 2 dx? du, isn't it? You see where everything came from there? That's not a look I'm convinced. What part of it?
I think I understand.
Do you know which part is hanging you up?
Where you go with the u to the u minus 1 equals 2x. Is this because you're trying to solve for the x, right?
Yeah, because in my integral, I can replace that with u. So I'm happy about that. That's going to be u.
That's the only thing that's
This is du.
You don't have.
This is x. I can't have an integral with u's and x's in it.
Okay.
So I need to somehow get rid of this x. The only relationship that I have anywhere that connects u and x together is this equation. So I just solved that equation for x. Now I have x in terms of u. That's going to get plugged in right here. That's the numerator now.
Now they're all u's.
Now everything has u.
If you factor a half out,
I'm going to take a half out.
you can take a half out, right?
Yes.
Yeah, flip it.
You don't flip it. So there's the 1/2. I'm going to pull it out. And then I have u minus 1 over u du. I need to stop buying these. They're good though. All right. Now what? What's the advantage of this integral over the one we had here?
You can split it.
You can split this one into two. Because now you have two terms on top, one on the bottom. So that integral becomes 1/2 integral, what, u over u is 1, minus 1 over u, du. And now you can integrate these term by term. So antiderivative of 1 with respect to u is u. The antiderivative of 1 over u is natural log u. So now I'm here. this turns into 1/2 u minus natural log u plus a constant. And then I have to go back and replace u with what u is. What is u? 2x plus 1. So this becomes 2x plus 1 minus natural log of 2x plus 1 plus a constant. But that was all just this integral, wasn't it, that I had done on the side? So I have to come back to my work that I kind of stopped at earlier. It's x natural log 2x plus 1 minus that whole thing. 1/2 2x plus 1 minus natural log 2x plus 1 plus a constant. And then it takes a little bit of work to get it to look like the back of the book, but you can. All right? Does that help?
Yeah.
Now, can I show you what the formula instead? The formula was so much better if you use the formula. So if we start this integral out, natural log 2x plus 1 dx, and we make the substitution u is 2x plus 1, right? Then what's du? 2 dx? I don't have 2 dx, I just have dx. So I multiply both sides by 1/2. 1/2 du is dx. Now rewrite the integral. What would this integral become? Integral, natural log u, right? Natural log u, and what's dx? 1/2 du. This is 1/2 integral natural log u du, and we came up with the formula for that last class. It was u natural log u minus u, wasn't it? So this turns into the 1/2, which is right here. It's going to come out. Oh, there it is. 1/2 u natural log u minus u. And then replace all your u's, plus c. Replace all your u's with 2x plus 1, and you're done. It goes a lot cleaner that way. Yeah, me too. All right.
Except for like on the answer in the book, it has minus x plus c.
I know. Well, they did some work on this. They distributed this through right here. 1/2 went here and here. Then this was a natural log, and this was a natural log, so they factored natural log out of those two terms and simplified. So that's what I'm saying. There's some simplification you can do to make this look like the back of the book, but we can talk about that. Maybe you can come by and we can work through that part of it. Okay. All right, well, we have lots to do today. We're still doing 6.1, all right? We plan to have a test a week from today, our first exam, all right? And it'll cover just up through 6.1, all right? So this section is where the test will end. Let's take a look at this classic problem. E to the x cosine 2x dx. Now, this is a variation of a classic problem. What hopefully you kind of took from doing your integration by parts homework was that what happens is you try and pick something for your u so that when you use integration by parts, you take the derivative of it and it gets a little easier in the new integral. Like if it starts out like an x cubed in front here, you pick that. When it goes through integration by parts, it becomes x squared. Then perhaps you have to do it again, and it'll become an x, and perhaps one more time, and it'll become a constant, right? The transferring of the derivative. Here we have an issue. Because if I take derivative of e to the x, what's it going to be? E to the x. And then derivative of cosine is going to be sine. So what's going to happen is no matter which I choose, when I go through my integration by parts, I'm still going to have an e to the x and a trig function. And even if I do it again, e to the x and a trig function. So what happens is nothing really goes away. But there's still a way to solve this problem, right? So check this out. First of all, let's realize there's no basic substitution we can do. Really, nothing in its derivative, really. So let's try.
Try like double angle?
You could try double angle. You could try it, but it's not going to make it any easier. You probably just go in circles with it for a while. Only because this e to the x is going to mess everything up. Pick something and then pick something, for u and pick something for dv. So for u, dv, I'm just going to take a shot in the dark here. I'm going to go e to the x for this one, which forces this one to be cosine 2x dx. Right? So I'm just taking a swing here. du is e to the x dx. And then let's see how many of you have got this down now. What's the antiderivative of cosine 2x? 1/2 sine 2x. Good. So now this integral becomes 1/2 e to the x sine of 2x, right? That's u times v, minus the integral of 1/2 e to the x sine 2x dx. So that's my voodoo right here. Agreed? We're all there? What's up? So this right here, these two, this is ultraviolet minus integral, this is v du. So that's this one and this one multiplied together. Yeah? Now let's look at this integral. And that 1/2 can come out, right?
Yeah.
So isn't that almost the same identical integral, except now I got sine instead? Right? So what have we done in class whenever we had an integral that required another, possible integration by parts? Just do it again, didn't we? So I'm going to, just to save a little space, I'm going to pull that 1/2 out of this integral real fast. There it is. And now let me do integration by parts on this. Okay? Let's do integration by parts here. My u is e to the x. My du is e to the x dx. What's my dv going to be? Sine. So dv is sine of 2x dx, which means what is my you know what I'm trying to say? What's my v? Negative 1/2 cosine 2x. Right? Any questions? So this is going to be a pretty long thing here to write. So here, I'm going to rewrite the whole thing. This is all equal to 1/2 e to the x sine 2x minus 1/2, but then this integral became ultraviolet minus 1/2 e to the x cosine 2x. So that's ultraviolet right there. Minus integral voodoo, v du. So what's that going to be inside here? Negative 1/2 e to the x cosine 2x dx. Close off my bracket.
So it's fine, we just start keeping a constant in the front, right?
I'm sorry?
Like it's fine, like if we start skipping steps and like just putting constants in the front.
What constant?
Well, like the 1/2, because you know how it's like 1/2 cosine, and you already like move dx to the front.
Yeah, I'm not sure I understand your question.
Never mind.
Okay. I didn't know if you were talking about the constant of integration, like the plus c, or if you were talking about something else.
So like the 1/2.
Oh, yeah, I see what you're saying. Yeah, I always pull my constants to the front.
Yeah.
Yes. And I'm doing all my e to the x's before my trig functions because that's kind of like what I've been doing the whole problem, like just staying with that format the whole way. It wouldn't be wrong the other way. It's like kind of like descending order with polynomials. That's the way we like to organize things.
The 1/2 in front of the e to the x inside the bracket, where did that one come?
That was from my table over here. I had u and I had v. U times v gave me this. So this is the u times v from the first integration by parts. This is the u times v from the second integration by parts. You follow? Okay. Now, let me distribute this negative 1/2 through. All right, and let's see what we get. This equals 1/2 e to the x sine 2x. Well, you know what? Before I distribute that, let me show you why I'm going to do this. Because right now, you might be saying, okay, look, I have negative 1/2. I can bring that out of the integral, right? Then what's still in this integral? E to the x cosine. And it seems like we're not getting anywhere here, right? It's like we're going around in circles. Y'all see what I'm saying? But isn't this integral, if I pull the 1/2 out, the negative 1/2, isn't this integral exactly the integral up here that I'm trying to find? So by doing integration by parts twice, I actually got the integral I'm trying to figure out what it is to appear on this side of the equation. And that is critical in this problem, is that what we're trying to figure out appeared again. So just bear with me now, okay? You just have to see this first time through. Here's this, right? I'm going to just distribute this all out. What should I get? What's this here? Plus 1/4 e to the x cosine 2x, right? Yes? What's this to here? Now, this negative 1/2 comes out, becomes what? Positive? But then you're hitting it with a negative. So it becomes negative 1/4 integral e to the x cosine 2x dx. Right? No one has a question on that? Okay, so watch what we got here. This is actually kind of cool. The original problem, integral e to the x cosine 2x, I'm going to have to write real small, dx equals 1/2 e to the x sine 2x plus 1/4 e to the x cosine 2x minus 1/4 integral e to the x cosine 2x dx. Right? That's what it is. My original problem is this, isn't it? It's an equation. So what I'm going to do is I should do it in a different color. I'm going to add 1/4 integral e to the x cosine 2x dx. Because that's a number, isn't it? Or it's a function, it's something. So I can add it to one side of the equation only if I add it to the other side, right? So I add over here 1/4 integral e to the x cosine 2x dx. Do you see that? What happens over there? Disappears, right? It's gone. On this side, how many integrals do I have here? One of them, right? I add 1/4 of that integral. That's 5/4, right? So what I get on this side is 5/4 the integral that I'm trying to find is equal to 1/2 e to the x sine 2x plus 1/4 e to the x cosine 2x, right? And then finally, to get my answer, I don't want this 5/4, so I multiply both sides by 4/5, the reciprocal. 4 over 5 here cancels, becomes a 1, right? Multiply each of these by 4/5, and you get integral e to the x cosine 2x dx equals, what's 1/2 times 4/5? We're taking 1/2, multiplying it times the reciprocal of that, 4/5, right? So 2/5. 2/5 e to the x sine 2x plus this times 4/5 is going to be 1/5 e to the x cosine 2x. And we know there's going to be a constant of integration. We can always have some constant out there, right? Okay, I have not shown you a problem like that before. So it happens sometimes that to figure out an integral, you actually have to make it appear, or it will somehow magically appear on the other side, and then you have to move it to the other side, add them together, and multiply by what you need. What do y'all think of that? I'm a little concerned with the looks on your faces right now. What's up?
I just missed one step. 5/4 on the outside, did you flip and multiply to the other side?
Yes, I multiplied this side by 4/5, which makes this a 1, but then I did 4/5 over here on this side, which means I have to multiply it through. So it just hit those two fractions in front. Y'all sure you're all right? Okay, integral 0 to 1. So we have a definite integral now. X squared plus 1 e to the negative x dx. Let's pick a u and a dv. How do I know that I'm using integration by parts? I don't see something as derivative, yeah. Pretty much. Well, I see what's the derivative of x squared plus 1? 2x? That's an x, but then that would be trapped up in an exponent. Remember, we don't want the derivative to be like somewhere complicated. We want it to be just sitting there. So yeah, substitution won't work. So we got to pick something. Let's pick something. Let's do it. What's the u and the dv here? X squared plus 1 for u. And dv means, that means it has to be e to the negative x dx. We don't have a choice. Now what's du? 2x dx, right? What's the antiderivative of e to the negative x? Negative e to the negative x, good. Negative e to the negative x. And that's just because a little bit of the chain rule. You have to account for that negative up in the exponent. So let's take a look at what this new integral becomes. This is equal to ultraviolet x squared plus 1 e to the negative x minus voodoo, which is x squared plus 1. Oh no, that's not right. Which is negative 2x e to the negative x dx.
Did you forget the negative in front of the e?
I think I did, right here. This negative times this, so this should be negative right in here. I'll put it right out front, okay? So negative x squared plus 1 e to the negative x plus 2 integral x e to the negative x dx. So I just pulled that negative 2 out of the integral. Any thoughts now? How do you mean cancel? You're kidding? Okay.
Do it again.
What do you think we should do then? Well, look what happened. Our original problem had a quadratic sitting in front of e to the x. Now we have a linear in front of e to the x. The power came down by 1, didn't it? So, do it again. U this time will be x, right? dv will be e to the negative x dx. I thought I said never let u be x. On substitution, that's what I said. On integration by parts, you may let u be x. Good. Okay, du equals dx. Antiderivative. So this is the same game we're playing, right? This is the same antiderivative up like this. Derivative of x is just dx. That integral is going to get a little cleaner, isn't it? Let me see if I can keep track of all my signs and everything on the next line. This is equal to negative x squared plus 1 e to the negative x plus 2 times, now my new integral is, not new integral, that integral becomes what? Negative x e to the negative x, right? That's u times v, ultraviolet, minus integral v du. So I'm going to have a negative, right? Negative e to the negative x dx. And that's done. And I can find the antiderivative of this, can't I? Because I don't have that x out in front anymore. We've actually already found the antiderivative of e to the negative x twice already, so we should be able to do that now, right? So if you want to, you can just forget about that and make it a plus sign here, however you want. Negative x squared plus 1 e to the negative x minus 2x e to the negative x. I distributed to here. What does all this become? Everything here, including this minus sign. What does all that become? So what's the antiderivative of e to the negative x? Negative e to the negative x, right? And then make it negative. So that's positive. Then make it negative. So it's negative. And then hit it with this. So minus 2. Let's see. Minus 2 e to the negative x plus c. Let me double check my work here. Yeah, that's right.
Yeah, that makes sense.
Okay. Now that's just the antiderivative. Remember we had definite integral, right? So now we need to evaluate at 1 and evaluate at 0. So therefore, what I want to do is I want to plug in 1 into this and then 0, right? And subtract. So I'm saving some time and space here. I'm just going to go straight to the two things like this. What do you get when you plug 1 into this first? So let's plug 1 in. Negative 1 squared plus 1 e to the negative 1 minus 2 times 1 e to the negative 1. Crap, I'm out of room. All right. Minus 2 e to the negative 1. That's just plugging 1s in for everything, right? For all my x's. Then minus, now let's plug in zeros. Negative 0 squared plus 1 e to the negative 0 minus 2 times 0 e to the negative 0 minus 2 e to the negative 0. What is this? What's 1 squared plus 1? 2. Negative 2, right? E to the negative 1. Yeah, e to the negative 1 is same as 1 over e. So I'm going to put negative 2 over e. That's this one right here. Minus what? 2 over e again. Then minus 2 over e again, right? Do y'all see that? Those are these three right here. They're all the same. And then I'm going to subtract from that. Let's see. This is 0 plus 1. That's 1. Negative 1. What's e to the 0? E to the 0 is 1. So this is negative 1. This one is dead. 0 times anything, 0. And this one is negative 2 times 1. So negative 2. These all have the same denominator, don't they? So don't you just add numerators up? What's negative 2, take away 2, take away 2? Negative 6 over the common denominator. Then this becomes what? Negative 1, it's negative 3, but then plus 3. That's your answer. Without turning it into a decimal, that's your exact answer. Negative 6 over e plus 3. What are your thoughts? Trying to get a feel for where y'all are, like how you're feeling about all this stuff.
You have to do double time every time? You have to do double it every time?
Not every time, no. But we shouldn't be surprised to have to do integration by parts twice. Yes?
I know to use 0 and 1 as your limits.
That was in the original problem. It was just the 0 on the bottom and the 1 on top. How about this one? See here I'm given the limits of integration right there, okay? Tangent inverse of 1 over x dx. This one's tricky. So no one answered my question. How are you feeling about all this? I mean, for those of you who've really been like trying and doing the homework and stuff, is it helping to? I know some of y'all are doing group studying together. I'm hoping that's making it a little easier. All right, this is a good problem also because, well, you'll see why in a minute. So basic substitution. Not really, right? There's nothing in its derivative just sitting there. So the only other thing we have is integration by parts. So I need to pick a u and a dv. And we don't have a whole lot of options here, do we? Whoa. As far as our u and our dv, what does u almost have to be here? The whole thing, right? The arctangent. Be careful, that's inverse tangent, arctangent. And that forces our dv to be dx. Now you need to know what the derivative of arctangent of something is. du. So maybe you need your formula sheet. What's the derivative of arctangent of u? That's tangent. 1 over 1 plus u squared, right? du. Derivative of it. So this becomes 1 over 1 plus u squared. But what's u for us? I mean, not u for us. In the formula for arctangent, the derivative of arctangent of something is 1 over 1 plus that something squared, isn't it? What's the something for us? 1 over x squared. Times chain rule. Now go inside arctangent. What's the derivative of 1 over x? So remember, 1 over x is the same as x to the negative 1. What's the derivative of that? Negative 1x to the negative 2, which is the same as negative 1 over x squared, isn't it? So I have next to this a negative 1 over x squared dx. Do y'all follow that? And then what's v? v is x. So my integral becomes, or actually, I'm going to do the indefinite integral first. So this becomes ultraviolet x arctangent of, not x, sorry, of 1 over x minus integral v du. I'll just write it all out. X times 1 over 1 plus 1 over x squared times negative 1 over x squared dx. Questions? I'm trying to clean this up because I'm looking at that integral and I'm kind of like, what the hell? How about plus, making it a plus because I have a minus and a negative in there. And what else can I do? That might clean things up here a little bit. Can I do this x divided by x squared, which would give you like just an x on the bottom? I could do that, right? So I have 1 over 1 plus 1 over x squared times, I still have a 1 over x dx. This is a tricky problem. That's why I'm showing you. I mean, at this point, you might kind of just be sitting there going, okay, what am I going to do with that, right? Yes?
What happened to the x squared on the bottom?
I did this x over this x squared and canceled and came up with 1. So when I first did this problem, just, I don't know, an instinct took over. I'm not sure where that instinct came from, just probably because I'd done thousands of integrals in my life. And I'm sure someone showed this to me at some point. First I rewrote this as 1 over x squared. So I actually squared the 1 over x. And then I looked at this over here, this 1 over x that I have here, and don't write that down yet, just don't write this 1 over x. This you can write. And what I said to myself is, I would love to multiply this x through here, which I can, right? It's multiplication. I can go straight across. 1 times 1, and then x would go to each of those terms, right? But if I multiply x times 1, I get an x. If I multiply x times this, I'm going to get a 1 over x, won't I? I'd really like to not have a 1 over x here. So it would be even better if I did x squared times this, right? Because what would happen? X squared times 1 would give me x squared, but then x squared times 1 over x squared would give me a 1. So I kind of said to myself at that point, well, wait a minute. I can make this an x squared by putting that back as an x. Well, see, your nature might want you to cancel that, right? But it actually turns out that you don't want to cancel it because you can multiply this through. Now, just watch where this goes by doing this. This equals x arctangent 1 over x. I have plus the integral, and then multiply that fraction across, and what do you get? What's on top? X on top. On the bottom, x squared plus 1 dx, right? That's what I get when I multiply this here, x squared, this here, 1, they cancel. On top I get x. And what's great about that integral? So you're seeing arctan, yeah, that's good to see that, but it's not that complicated. Doesn't even have to be that complicated. I've heard it. It's just a basic substitution. Do you see something in its derivative? X squared plus 1, what's the derivative of that? 2x. And you have it, you're off by a constant. See it? So here I just make a basic substitution. U is equal to x squared plus 1. Du would be equal to 2x dx. I don't have 2x dx, I actually just have x dx, right? So I'd have to multiply both sides here by 1/2. And now I can rewrite that integral. So what does this integral right here become? Integral, what's x dx?
U over U.
It's 1 over u.
That's 1/2 du, right? So 1/2, here's du, and then I would have the u on the bottom, so 1 over u. And what's the antiderivative of this? Natural log of u. So this integral is going to become x arctangent of 1 over x plus 1/2 natural log of u. But what was u? X squared plus 1 plus a constant. So because this right here is a basic, this right here is a basic substitution, I'm not going to go through a whole bunch of the detail of all this. You could figure that out, hopefully, and that's just this last part right here. We're not done, though. Why? Limits of integration. So now we got to plug stuff in. All right, I'm going to plug in now. What goes first? What gets plugged in first? Root 3. So I've got root 3 arctangent of 1 over root 3 plus 1/2 natural log of root 3 squared plus 1, and then minus, we get to plug in 1 now. 1 times arctangent of 1 plus 1/2 natural log of 1 plus 1. And the reason why I like this problem right now, I wanted to get it to this point, is to figure out if you could tell me what the arctangent of 1 over root 3 is. So for those of you who are real good with your unit circle, you're trying to figure out what angle, when you take tangent of it, you get 1 over root 3. And remember, tangent is the y-coordinate divided by the x-coordinate. So where on your unit circle is the y-coordinate divided by the x-coordinate equal to 1 over root 3? It's the same place that you have 1/2 over root 3 over 2. 1/2 over root 3 over 2, if you do the reciprocal or cancel the 2's, however you want to look at it, gives you 1 over root 3, right? So where is your y-coordinate 1/2 and your x-coordinate root 3 over 2? That's the other way. This is your y-coordinate, this is your x. Pi over 6. Pi over 6. So this is pi over 6. Right there. Then you have your root 3 in front times blah, blah, blah. This is just 3. Right, when you square root, you get 3 plus 1, that's 4. So that's natural log 4. Over here, what's the inverse tangent of 1? So pi over 4. Pi over 4. That's because your x and your y coordinates are the same there. So y divided by x is 1. So this one becomes pi over 4. Okay, this is number 22 in the book. So I posted the solutions, right? For those of you who saw it, all the even problems are worked out. You can go through and see how everything plugs in and what answer you get there. All righty. 24, I think, is worth looking at. We might not go through the whole thing, Integral. Look at the solutions online. I don't want to work through any more of that one. So there's a couple of ways to work through this problem right here. All right, there's a few ways to actually attack this one. The way that I attacked it is I tried to say that I saw something in its derivative. Like the 4 plus r squared, I said the derivative of that is r. Well, 2r, right? But I have r cubed. So what I did is this. I turned the integral into this. R squared times r over square root of 4 plus r squared dr. Now if I make a basic substitution, u is equal to 4 plus r squared, then what's du? 2r dr? Do I have a 2r dr? I have r dr, don't I? But I don't have 2r dr, so I need to multiply by 1/2 on both sides. And then I'm going to need r squared, which I can take this and solve for r squared, which is u minus 4. You see all that? So what does this integral become? Integral, what's r squared? U minus 4 over, what's this? Square root of u, right? Yep. And then what's r dr? Is 1/2 du. What's good about that? 1/2 can come out. 2 terms on the bottom, on the top, 1 on the bottom. You can split it into 2 integrals, can't you? And just use power rule on each one. Okay? Man, that's really nice that way. I did it different on my solutions. I did integration by parts. Which was much harder. But the key to me showing you this problem, the reason why is because I want you to see how you can always pull these things apart and get what you want, and part of it use it here, the other part of it use it somewhere else. Okay? Just be aware of that sort of attack, that sort of technique. Now, let's try this. This is an integral that's going to come up in the next section, and I don't want us to have to deal with it there. First, do you know what the antiderivative of secant x is? Secant x. Antiderivative of secant x? Is it on your formula sheet? Secant x? It's there, right? Okay, so if you wanted to figure out what the antiderivative of secant x dx is, you could use integration by parts to show it. I'm not going to. I want us to do this one because it's going to come up in a next section. What's the antiderivative of secant cubed x? So watch this. I'm going to do a u. Oh, I need to stop my video.